Yeah, I think when I originally pitched this talk, I called it 5 Tricks for High-Performance Geometric Algebra, but I've got a little bit carried away in the last few days writing it, so it's increased. I had one last night, so it increased again. Yeah, a little bit of background about me. So I haven't been attending GA conferences for a little while. I took a sort of break, but I'm kind of back now. I've been researching geometric algebra for quite a long time now. I started back in 1990. I started my PhD, and yeah, it's on. Okay. Yeah, is it not loud enough? Do you want me to shout? I think I attended my first geometric algebra conference in 1991 in Poland, along with David Hestenes and Stephen Anthony. One of the key things that I sort of say to people now, the sort of lesson from my own research time, was pick a problem to work on first. Don't say I'm going to do research into geometric algebra. I get asked that quite a lot of the time. People say they want to come work with me to research geometric algebra. Kind of doesn't mean anything. Pick a problem, pick an algebra that's going to be useful for it, and use that to help you solve your problem. Around 2004, 2005, I was getting a little bit frustrated with life in academia, so I spun out a company called Geometrics that went on to work on this global illumination problem in the games industry. We got a solution running for computing the bounce light in real time in a 3D world, which originally ran on PlayStation 3, which kind of at the time was thought to be pretty much impossible. By 2012, we had the same solution running on an iPhone, so we were doing global illumination on an iPhone. And this was something that people thought was the domain of extremely big ray tracing farms. So to see it done a completely different way on such small hardware was quite revolutionary. That Enlighten software, as I say, found its way it became the main global real-time GI solution for Unity. It was a lot of our customers using the Unreal Engine, came the standard in Frostbite, so all of the Electronic Arts games used it, still do use it actually. And it was used in hundreds of games in the end. But in the end, we were acquired by Arm. It's the way the industry works. Small companies get acquired by big companies. Big companies then generally mess up what was good about the small companies, and the technology kind of dissolves. But a bunch of the team is still there, and some of the team have actually moved on with me to work on a couple of new projects. I left Arm in 2018 and have spent most of the last few years mixing research with advising some new startups. And there's 2 companies I'm spending most of my time with at the moment that might be of interest to some people here. The first one is Monumo, who are kindly sponsoring a lot of my work on GA at the moment. This is a new Cambridge-based startup. We are applying AI techniques to design more efficient electric motors, predominantly focused on EVs, but also pretty much anywhere you see motors, generators. We want to come up with some far, far better designs than is currently possible. And a key step in that is having extremely fast simulations, which is where we're using GA in our toolchain at the moment. So we can simulate the electromagnetic fields very fast, and that gives us a handle on how to design more efficient motors. And if you look at how motors are designed currently, it's a few engineers sit in front of some Autodesk products, something like that. And they can churn through a few designs a day because it takes a long time to get the results out. We're now churning through hundreds of thousands of simulations and then using AI to help us drive those simulations in directions of more promising designs. So that's very exciting, and not surprisingly is a hot topic for investors, so it's going pretty well. The second company is an interesting one. They approached me from Cardiff, but not from the main sort of technical university in Cardiff. They approached me from the art university, as it were. Actually, it's the one where a lot of games developers learn. A team there have developed a proposal for replacing projective geometry in the graphics pipeline. If you are if you've played around with the graphics pipeline, you'll know that it's got projection geometry kind of baked into the way the thing works. And that basically means that once your field of view gets above about 100 degrees, you start getting distortions at the edges. So you're actually limited to quite a narrow field of view. What Fovotech have developed is a way of opening up the field of view so that you can get to about 150 degree field of view without those nasty distortion effects. You can get some really interesting, good-looking images. And you can do that still in real time. They've got it implemented in Unreal and Unity at the moment. So that's getting a lot of interest, partly from games, actually more from sort of architectural visualization spaces and film CGI. But the effects are quite stunning. If you play a first-person shooter with this turned on, after a while you kind of get used to it. Off, it's like you've got tunnel vision, that you're stuck with this very, very narrow field of view. You want to get everything back. So I think it could be a really interesting next step in gaming. I hope, anyway. I'm currently, my own research topics are, along with the stuff of these companies, discrete geometric calculus. This is something I've talked about at conferences for years. I wanted other people to develop it. They haven't, so I'm having to do it myself. But it's what we're starting to use inside Monumo. And when I left academia, gauge theory gravity was kind of my thing with Anthony. So I'm back doing that now. It's nice to come back to. It's like going back to an old girlfriend, I suppose. So I knew I was the last talk, and I knew that today was going to be a very, very dense program where a lot of information has been thrown at you. So I was trying to figure out how I can tell you something useful, given that pretty much everyone here has seen too much and is probably quite tired. So I'm going to tell you some stuff that I would not normally show, because I want you to forget about it as soon as you've seen it, because it's largely useless. At least this first bit is, but it at least makes a point that is relevant for optimization and some of the thought processes I've been through for optimizing stuff. So we've done lots of stuff about the geometry of the objects we can create inside geometric algebra. This is a little bit more on the algebraic side. So how do we actually kind of write algorithms that can do these manipulations as optimally as possible? So we'll just start with a very, very simple little thought experiment, just given our 2D algebra. So 2D algebra has got scalar 1, 2 vectors, E1 and E2, and it's bivector E1, E2. And the one thing, hopefully, you've learned so far today is that E1, E2 squares to -1. It's like an imaginary number. Now, as soon as you have an algebra with objects that square to 1 that aren't the identity, immediately something should start sort of triggering in your mind that there are some interesting things you can do with that. In particular, you can define projection operations like P plus and P minus here. So I'm going to pick out E1 because E1 squared is 1 because it's a vector, unit vector. And if you define P plus and P minus, so P plus, for example, is a half 1 plus E1. If you square that, you get a quarter 1 plus E1 all squared. Expand it out, you get 1 plus 2E1 plus E1 squared, which is 1. And you get back to P plus. So you get something that squares to itself. If it squares to itself, that means a number of things. First of all, it can't have an inverse. Because if it did, you could multiply through by that and prove that the thing was 1, which it isn't. So we're starting to get these things that are non-invertible, which is obviously going to happen in geometric algebra because there are only certain algebras where everything's invertible. And if you look at, say, P plus times P minus, you get 1 plus E1 times 1 minus E1, which difference of 2 squares is 1 minus E1 squared, which is 0. So these two things annihilate each other. That's the really interesting point. It means that you can define things in your algebra that when you multiply them together, you get 0. And that gives us an optimization trick. This is the way I'll think about it at the moment. This is a sort of optimization trick. Then we'll come back to what this means. We can take an arbitrary object, and we can use the fact that P plus plus P minus is 1 to just put two factors of 1 on either side, and then decompose the object down into these four terms. So again, it's pure algebra. There's no geometry here. And by the way, actually, this thing of adding a scalar to a vector, I'm quickly going to ditch that as being useless. But if we look inside that sort of sandwich with one of these projection operators on either side, you see that only a certain number of things survive. So E1 times P plus is P plus, so you can drop all the E1 terms, you just get a scalar out. And if you put, say, an E2 between two P pluses, that annihilates, you get 0. And similarly, an E1, E2 in there gives you 0. And when you kind of track through that, you see that given an arbitrary A, there are 4 numbers that you can sit inside one in each of those 4 sandwich possibilities, which are slightly suggestively labeled A11, A12, A21, and A22. Same for B. Obviously, this all looks horribly ugly. There's no reason to actually do this. But now we're going to multiply these things together. So remember, in this case, A and B are completely arbitrary elements, multivectors in this 4D algebra. So multiplying together 2 things with 4 terms in each, so it should be 16 multiplications to do. Okay? But when we put these together and use the fact that some of these P pluses and P minuses are 0, you find that actually you only get 8 multiplications to do. And we've discovered something. We've actually invented a new type of product here. If I put my A's and B's into this funny structure here and multiply them together where the columns, the rows of A multiply the columns of B, you get exactly the correct terms. Only 8 multiplications to do, and we get this quite compact representations. So obviously what we've done here is we've rediscovered matrices. They're a kind of optimization trick for doing geometric algebra calculations. That's kind of how I like to think about matrices. And we've also, as a byproduct, constructed a standard matrix representation for G20. So this doesn't sound particularly impressive, but actually, factors of 2 matter in a lot of code, particularly if you're trying to write anything optimal. And if you're trying to multiply together general geometric algebra elements, you need to sort of take care of this. But also, part of the reason I want to talk about this, it was partly inspired by, I think, Stephen's original poster about getting rid of matrices, is if we actually look at the historical timeline, matrices aren't that old. Matrices were introduced in the 1850s by that guy, Cayley, the multiplication table was named after. And Clifford introduced his algebras only 30 years later. And also, the 1850s was also the time that Hamilton was introducing the quaternions. So they were all kind of in the mixture at the same time. It wasn't the case that matrices came first and then everything was built on top of them. Interestingly, something I didn't know until recently is that Cayley had just been appointed a new professor of maths at Cambridge just when Clifford arrived there as an undergraduate. So Clifford attended Cayley's lectures, and unfortunately Joan's not here now. She was telling me over lunch that in the Trinity Library they've got records of letters that Clifford wrote to Cayley. So obviously they all knew each other. But it kind of begs a really interesting question that I like to ask about maths quite often. What if this chronology had been reversed? Clifford didn't need Cayley's matrices to come up with his algebra. If the timelines had been slightly different, we could easily have had geometric algebra first and matrices second. And then we'd be asking, well, how do you construct matrices in terms of geometric algebras? We wouldn't be thinking so much, well, how do we construct geometric algebras in terms of matrices, which is the way it's often presented. I talk about this quite a lot when I talk about geometric algebra to sixth formers, people sort of preparing to come to university. I like to give the talk about G20 and motivating complex numbers. And it's all you need to do to motivate complex numbers is have this idea that orthogonal vectors anti-commute. That's all it takes. And it's not actually a big step to imagine that we could have got to complex numbers via that route before we got to them via solving quadratic equations. Because actually, how often do you really need to solve a quadratic equation? It's not that exciting a problem. But dealing with geometry in 2D and 3D is something that engineers and people were really focused on. So I do think a lot of the chronology of math is a lot more accidental than we realize. But we always kind of teach math as this logical progression from real to complexes, etc., all based on the historical timeline for when things were discovered. Anyway, so that's just an aside. It turns out this is a result partly due to Cayley. Every associative algebra, So every geometric algebra has a matrix representation. And in the sort of mid-20th century, somebody sat down and worked them all out for every possible geometric algebra, every possible Clifford algebra. And this is the basic table. We only need to, I'll explain in the next slide why we need to go up to total size 8. But on here, there's some interesting cases to look at. This M means a matrix of size 16 or 8 or 4. And then the thing in the brackets is matrix over real, matrix over complex. Or, rather curiously, we get these matrices over quaternions. That's actually a little bit surprising in some sense. It's not how we typically do representation theory in maths. Usually we work over reals and complexes, and we treat quaternions as sort of two-dimensional complex matrices. But they're absolutely baked into geometric algebra. You see quaternions all over the place. Some sort of notable ones here, 2 by 2 G20, so 2D is 2 by 2 real matrices. 3D, the Pauli algebra was mentioned before lunch, is 2 by 2 complex matrices. Space-time algebra is actually 2 by 2 matrices over quaternions. And the conformal, so 4, 1, is P plus Q is 5, 3, it's 4 by 4 matrices over complex numbers. And if you want to go and implement a geometric algebra computation, you can use this. Okay, so this is the point where you can now forget about all this stuff, because this particular table itself, it's sort of interesting, but it's not the key to writing optimal code. But it is useful to know. Here's a quick summary of some of the results there. Other things to point out, the matrices are always powers of 2, because the total number of elements in the algebra is always a power of 2. The even dimensional ones are always over the reals or quaternions. The balanced one, these ones down the middle, which are sort of particularly interesting, they are always matrices over the reals, and they just kind of get bigger and bigger. In odd dimensions, the representation depends on the square of the pseudoscalar. If the pseudoscalar squares to -1, you get a representation of complexes. If it squares to +1, you get a pair of real representations. And actually, those pairs of real ones are kind of nice, because there's some computational efficiency there. One other thing to mention, in the pure maths literature, when people talk about something called a spinor, they're imagining those matrices acting on a column vector of some particular size. That is one way to think about spinors. It's kind of the old-fashioned way. It's not how we tend to think about spinors in geometric algebra. What's really interesting, though, I think much more interesting than those matrix representations, are the relationships between algebras. They are ways to jump from one algebra to another. And this is kind of one of the messages I want to kind of bring home to people. Don't fixate on working on one particular algebra. You should learn how they all relate to each other. You should learn how to jump between them. There are two particularly useful ways of jumping. One is this thing called the evens or projector split. So the even half of any algebra is a geometric algebra in its own right. And there's this relationship here that tells you that the even subalgebra of PQ can be one of these two. It could be GP minus 1 or GPQ minus 1, depending how you do the split. Similarly, you can split you can use what's called a conformal split, where the algebra, say, GP plus 1, Q plus 1, is the product of the algebra GPQ and G11. This was what David talked about briefly in the paper that he published, in his book, actually, that we all kind of missed for about 20 years. And if you track all of this through, you find that you can remove multiples of 8 from every algebra, and then the big algebra is just 8 by 8 matrices over the smaller ones. That means that, and the fact that GP plus 1, Q plus 1 is 2 by 2 matrices over the smaller one, means that for anything larger than 8, you can always figure out the smaller algebra of size less than 8 that the representation is done. So this table has done it all, because all the larger ones you can extrapolate from there. Okay, so what is all this useful? Where is all this useful in actually writing some optimal code? So what these matrices do is they encode this trick that certain things can multiply, can annihilate each other when you multiply them together. So if you're taking general elements, you can't do better than this type of way of multiplying things together. But what we can do, rather than implementing those large matrices, is we can use a trick where we only focus on the even half of an algebra. So we're going to use this even split in particular. First of all, just going to explain exactly how it works, because this also raises another interesting point, and I think sometimes gets forgotten in the field. The way this works is you go into your PQ algebra. Let's say it's all the generators Euclidean, they're E1 up to En. And you pick out En, and you multiply all the other n-1 generators by that. So you've got a new set of bivectors in this space, capital EI. When you form the symmetric product of those new generators, they also satisfy EIJ plus EJEI is, in case, minus 2 delta IJ. They are generators of a geometric algebra. They anti-commute with each other, and they square to plus 1 or minus 1. And so they generate a new algebra, which is the algebra of the even subalgebra of the large one. And it defines this embedding, in this particular case, G0 n-1 is embedded inside Gn0. This is not the kind of the obvious embedding where if you had, say, E1, E2, E3, E4, you just pick out E1, E2, E3 and make them generators. It's a different type of embedding, something that David Tessie's likes to call the projective split. And one thing that's really worth remembering here is that this grade concept that we talk about a lot is actually quite subjective in many cases. In this particular case, these capital EIs, they're grade 2 if we think of them in GPQ, but as generators for, say, GQP minus 1, they're grade 1. Grade depends on where the thing is embedded. So sometimes people get a little bit fixated on the types of grade and what the grade means, but grade's a little bit more of a flexible concept than you might think. Okay, so how does this all relate to actual implementation? So there are basically 2 ways you can go about trying to implement geometric algebras numerically. There's the geometric product first way, which is the way I tend to prefer, and there's the kind of inner-outer product first way. The geometric product first way, you really want to implement something like those matrix representations, because if you don't, you're missing all these factors of 2 that you can halve the computation by. That's very good for doing multiplying rotors together, for example. It's less good if you just want to do, say, a vector, an outer product vector and another vector giving you a bivector, because you may be doing some wasteful calculation. And actually, this does become unfeasible for larger algebras. It's something else that we kind of don't talk about too much with geometric algebra, but once you get above a certain size, you can't even begin to store these multivectors. If you're looking at, say, a 64-dimensional space, where I could quite happily write with vectors and bivectors in that space, but if you try to write down a rotor in that space and store it, there isn't enough storage in all the compute facilities on the planet. So this is not a good idea for large algebras, but it's a very good idea for small algebras. The other way is you build up a whole library where you store vectors as an object, bivectors as an object, 3 vectors, 4 vectors, and implement all sorts of different product rules between them. Quite painful. But in some sense, that's the only way to do the much larger algebras. So I'm going to talk about ways of doing both of these. And I think the switchover point where the first approach starts to get a bit too slow is around 6 dimensions to 8 dimensions, somewhere around there. When the matrices start getting up to about 8 by 8, you start to worry that there's a bit of computational overhead there. So this is the first of the tricks. When implementing a general geometric algebra and implementing a geometric product first, We're going to use some version of those matrix representations. But what we don't really need to do is implement the entire algebra, because in every practical implementation, you are never going to add an even object to an odd grade object. All of the useful applications have things of a particular grade, so say vectors, bivectors, whatever, or things like rotors, which are all even. But aside from that stuff I did at the start, which is all nonsense, you would never add a scalar to a vector in a useful application. There are one or two counterexamples. The most relevant counterexample would be the E and B fields, where you do combine them, but actually you shouldn't be in 3D when you're combining them. You should be up in space-time algebra anyway when you're combining them. So we don't need to represent the algebra by its full matrix representation. We just need to get the matrix representation of the even half of it. And we need to define some map between even and odd elements. And then we can implement a much more efficient product. In fact, we implement 4 products. Even, 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 odd, odd, even, and odd, odd. So I'll just run through some examples of this. The particular library that I've been working on is all implementing this in Julia. Just out of interest, any Julia programmers here? Okay, I will not talk too much about Julia in that case. I like to try to keep the implementation as sort of clean and simple as possible, which you can do with the geometric product first implementation. So what you do is you just implement a formal multiplication operator. Julia allows you to overload the star operator, so you're not going to do anything other than that. So you need a product and you need a projection operation. So you need an operation that you can take in a multi-vector and project out the grade 0, 1, 2, 3, 4 bits of it, whatever. That's already enough to do pretty much everything in geometric algebra. You don't need to implement a separate dot or inner or outer products, because you just take a geometric product and project out the bit you want. What you do also need, though, is some way of getting numbers out of the geometric algebra. So you need the scalar part to return a number rather than a thing inside the geometric algebra. I've overloaded some operations in Julia, so actually I use trace from linear algebra to take out the scalar part. And it's handy to have a separate dot product that takes the scalar part, so it's sort of A-B scalar part projection. And you need reverse. And again, Julia has this nice multiple dispatch thing, so you can overload the tick operator, the adjoint operator in linear algebra. So R tick is R reverse. It means what you can do in Julia, which is a struggle in some other languages, is your code looks very, very much like your handwritten geometric algebra work. You can actually go further in the space-time algebra, for example. The generators are all gammas, and Julia actually typesets them as gammas, which is quite nice. So we need to implement the even subalgebra of G20, it's the first example. Look at our little table. The even subalgebra is G01, which is a complex numbers, which is exactly what you expect. You're in two-dimensional algebra. You've got scalars and bivectors, a bivector squared minus 1, so they are complex numbers. Indeed, I think, to me, that is complex numbers. It's not just a representation. That's where complex numbers come from. So, under the hood, the implementation is then very simple. For even elements, you just store a complex number. For odd elements, you don't store the odd element. You store E1 times that, because that maps it back to an even element. So you have two types of struct, but they've both got the same things in them, both got complex numbers in them. One for even, one for odd. And you implement the products between them. So even is just a complex multiplication. For odd ones, you've just got to put a star in various places where it's needed. And then reverse for the even is complex conjugation. Reverse for odd doesn't do anything because they're only R vectors, they reverse themselves. And once you've got those operations defined, that's basically it. The rest of it is all the sort of usual fluff that goes around some library code, but implement that and you're basically done with your 2D geometric algebra implementation. And you can just kind of think of it, it's basically a kind of wrapper to make complex numbers more useful, because it includes the ability to do a proper geometric product. G30, this is one where if you implemented the full algebra, you'd be doing Pauli matrices, so complex 2x2 matrices. But by just implementing the even part, you're actually back with quaternions, which is, I think, is more natural anyway for 3D. So your underlying representation for 3D geometry is a quaternion, and for the even elements, and in any odd dimensional space, the map between even and odd is always done by the pseudoscalar because it's nice and easy to do. So you store minus I3 times your odd elements as a quaternion, and then all you've got to do when you implement the products is put an appropriate minus sign in the product of two odd elements. And that's G30 coded up. And you can start doing some speed tests of this. And actually some of the results are really surprising. It's a really good lesson that just trying to count multiplications is not a good measure of performance on modern hardware. You really need to actually do some proper calculations and just time them. And Julia has very, very nice libraries for timing things. It takes care of a lot of the sort of hard work for figuring out when start and stop times are. So, for example, just doing some timings on this laptop, a floating point multiplication takes 25 nanoseconds on this. A quaternion product takes about 35 nanoseconds. Even though that's doing 60 multiplies compared to 1, it's only a little bit slower than one floating point, because the compiler does clever things with using SIMD, and you're able to sort of store up the calculations. You can take advantage of some latency in there. And a few surprising things here. So in 3D, the sandwich operation, R reverse, to do a rotation, which is quite a few multiplications, and I've always thought is a little bit slow. That whole thing takes 50 nanoseconds. If you go into Julia and code up a 3x3 matrix, let that act on a 3-component vector, that takes 90 nanoseconds. It's actually slower than the sandwich product, which I was very surprised by, because the sandwich product you think should be more complicated. It's certainly got more multiplications in it, but that's not naturally a good measure. Another kind of interesting comparison was the cross product versus multiplying two quaternions and projecting out the bivector part. Because you think, okay, I'm doing more multiplications with the quaternion case, but actually, Q1, Q2, and project out the bivector part is 60 nanoseconds, whereas the cross product was built into Julia was 90 nanoseconds, so slower. Don't really know why. These things are really, they're so deep down in the hardware, you don't really know, but we're getting some nice sort of very, very optimal behavior here. And the really curious thing, and this is something that I think there may even be possible to do better, is that quaternion product takes about 30 nanoseconds. Projecting out the bivector part of it takes another 30 nanoseconds, because the bulk of the time is in allocation, which seems a bit wasteful. I feel like I might be able to do something even better there. Seems odd to take longer to sort of get less numbers out. But this is clearly a good it's a good start for something that's pretty optimal, and it's going to stay optimal for these sort of smaller algebras. So I've very pointedly called G40 the projective geometry algebra, because this is the algebra that you would do projective geometry in, and David Hesnes did do projective geometry in when he wrote about it. Joan was doing it for spherical geometry, but it's the four-dimensional Euclidean algebra. It's kind of the algebra of the projective stuff that goes on under the hood in OpenGL and DirectX and that sort of thing. This is quite a nice one to be in, because if we look at the even subalgebra of G40, the pseudoscalar there squares to +1, not -1, so it's not built over the complexes, it's built over two copies. And we get, because it's a thing that squares to +1, we get those things I showed at the start, those decomposition projection operations. They work again, and they halve the amount of work further. So actually, in this algebra, the representation is a pair of quaternions, and when you multiply them together, you just multiply each quaternion in its own slot. There's no kind of cross terms to worry about, so it's very efficient. So this projective geometry, like this G40, you end up storing a pair of quaternions for the even elements, and the map from even to odd is this usual projective split, as David Hesnes would call it. And again, this is extremely fast. So again, sort of still way down in the nanoseconds. Next one of interest is G41. So this is a conformal algebra. It's the one that Joan was talking about, and this is the one that has PGA embedded in it. The plane-based geometric algebra is embedded in this. So again, we look at our matrix table. The even subalgebra of G41 is actually G40, and that can be implemented as 2x2 matrices with quaternion entries, which is the way I've done it in the Julia code. And actually, you don't even bother to implement 2x2 matrices. You just unwrap that. Those calculations is much easier. There is a question in my mind about whether this should be implemented as quaternions with 2x2 matrices as coefficients, but I suspect that'll be slower. But I actually do need to do some speed tests on that. So again, this is a very easy one to implement. 2x2 matrices over quaternions, odd dimensions, so the map between even and odd is on the pseudo-scalar, which squares to -1 in this case. And because I didn't want to get into any fights about notation, I just labeled the two extra dimensions, E4 and F4, E4 squared to +1, F4 squared to -1. And everyone can knock themselves out with their own favorite notation for n and n bar, or E0, or N0, or N infinity, or E infinity, or whatever combination is you prefer. And inside this conformal geometric algebra, we do have this subalgebra of elements built from the E1, E2, E3, the Euclidean vectors, and the point at infinity n. This is the sort of smaller PGA part. So to represent the entire CGA, even part, we're using 2x2 matrices of quaternions. Obviously, to get to the PGA, then, we just need a pair of quaternions, or a dual quaternion. So for PGA, we can implement this with the even elements given by quaternion pair, a dual quaternion, and the even-odd map, the natural thing to do here is to do that with a I3, the three-dimensional pseudoscalars at E1, E2, E3. The one extra thing we also need to implement in PGA is a dual, the PGA dual, which is this slightly clunky mechanism for enabling you to sort of grab numbers out. But that's actually no effort. It's just a couple of reverses and sign changes inside your element, so it's very fast. And again, so I was doing some more speed checks on this just to check out how PGA, CGA all kind of compare with each other, how G40 compares, and also how they compare with the matrix routine. So inside PGA, we can do a sandwich, an R reverse, so that would be a transformation of a point or a plane, etc. That takes about 70 nanoseconds, which is fast. And again, compares favorably with the 4x4 matrix acting on a vector, which takes 100 nanoseconds. The product of two rotors in this space, so that's the combination of two dual quaternions to get a new one, is about 30 nanoseconds. No, actually, no slower than doing one quaternion multiply, which is kind of odd. That compares very favorably with about 200 nanoseconds for multiplying two 4x4 matrices together in Julia. Similarly, you can do a projection operation here, so we can look at, say, two planes multiplied together to get the line between them. That's about 60 nanoseconds. If we kind of compare them with CGA, just the fatter algebra, that R reverse sandwich, say 70 nanoseconds in PGA, about 100 nanoseconds in CGA. So going from CGA to PGA is a speed up, but it's maybe not quite the sort of big order of magnitude speed up you might have expected. It's a bit more modest than that. And a rotor-rotor composition in CGA is about 50 nanoseconds compared to 35 nanoseconds. So again, some advantage to PGA, not huge. You can also kind of compare with projective G40, where that wedge product, say intersecting, well, let's say we're going to intersect two planes to get a line, that's about, say, about 60 nanoseconds in PGA, about 30 nanoseconds in projective in G40. So G40 potentially has some advantages in some cases there. Obviously, what you lose in G40 is this very nice feature that rotors in PGA are Euclidean transformations. So if you wanted to do a translation thing, you'd be back using 4x4 matrices in G40. And worth emphasizing, this is a 6-7-year-old Dell laptop, so the absolute timings don't matter a great deal. It's more about the comparison, but these are nanoseconds, right? This is really, really fast stuff. I wasn't sure if we needed a break here, but should I just keep going? I'll keep going, okay. Couple of other sort of, I've implemented a whole bunch of algebras, and one of the nice things that Julia has is a thing called multiple dispatch, where essentially you keep overloading the star operator, and it does, as soon as it sees something times something else, it just looks at all the various instantiations it has for multiplication and does the right thing. This means that you can have all of the algebras in flight at the same time. So there's no reason for your session to be like the way we used to run inside Maple, for example, where at the start you say, right, I'm in the STA, and then everything's done in STA. You can have all the algebras in flight at the same time. You can easily move between CGA, PGA, G40, etc. And if you want to squeeze the last bits of optimization out, you can pick and choose the right one for the right calculation. I don't know if it's possible to do that automatically. Probably with a bit of thought, but certainly you can easily take a CGA expression and think, okay, now I just want to drop into PGA and do that, and vice versa. So hopefully it removes some of the sort of fighting about which algebra is better in some particular cases. I also implemented line geometry. It's one that I quite like, this G33 algebra. It's one where null vectors now represent lines in three-dimensional space, and you can do quite fun stuff with that. And the final question, which I'm going to answer on this slide anyway, on the next slide, if we look at the main algebras of kind of relevance to three-dimensional geometry, we've looked at the three-dimensional Euclidean space, G30, that's implemented with quaternions. We've looked at G40, so projective geometry. That's implemented with a pair of quaternions. We've looked at PGA, implemented with a pair of quaternions. And we've looked at conformal geometric algebra, which is implemented as a 2x2 matrix of quaternions. So I spent a long time advocating to hardware guys that they should try to implement all sorts of geometric algebra stuff in hardware. I completely changed my mind now. All I want the hardware to do is give us quaternion multiplication as fast as possible. Everything else we can take care of. Geometric algebra will organize that into sort of sensible ways. But you just give us the fastest possible quaternion multiply, and we're kind of done. So in any time that you're in conversations with a hardware guy, and they're asking about what they could do to implement geometric algebra efficiently, just tell them that. Just say, just want quaternions. I want to be able to quaternions in as few clock cycles as possible. Hopefully, there's a lot of them in parallel as well. That'd be nice. Okay, so that's the kind of the core philosophy of this low-level Julia library I've written. But that only does algebras up to 6 or so dimensions. If you want to implement a more general algebra that can go up to much larger dimensions, that's when you have to ditch the matrix representation idea. You need to go back to some way of storing blades and their values. This is something I'd written a long time ago in Haskell. Lots of people have written their own versions of this. In fact, I think for a lot of people, the way you learn geometric algebra is you write your own GA library. It's kind of natural. That's what I encourage people to do. And generally, the way it works in Haskell was your key object is a thing representing the blade and the value. And a multi-vector is just a list of them. Actually, Haskell works with linked lists, which unfortunately is very, very slow. So I wrote some libraries doing this in Haskell. It was only when I started porting them to Julia that I learned how slow this was as an approach. The biggest issue with it in kind of Julia language is that you're working with an array of structs, and that's bad. What you want to be working in with a struct with arrays inside it. That's much more efficient, it's much more hardware friendly, much more parallelizable. So I've been working on implementing the more general case by flipping things to this struct of arrays approach and coming up with a new way of solving the hard part of the problem when you multiply together two blades, which is actually getting the sign right. So I'll explain why this was hard and the sort of the solution I've got to this now. So the way I tend to represent the blade, this is a fairly standard trick. I was first shown it by Steve Gall a long time ago, is you can represent a blade by a binary number. For flexibility, we like to implement mixed signature. So we had a scheme where binary number 1 is E1, then the next slot is F1, which is something squares to -1, E2 squares to +1, F2 squares to -1, and so on. You don't have to do that. If you just want to implement a large Euclidean algebra, you could just make it E1, E2, E3, E4, and so on. But basically, each blade then is just encoded by a binary number. So the really nice thing about that is that when you're multiplying two of these blades together, the resultant blade is just an XOR, binary XOR of those two numbers, because the only way that a blade can survive is if it's in one and not in the other. The only way a vector can survive is if it's in one and not in the other. So that's really easy. Binary XOR is obviously going to be very fast and easy to implement. The hard part is getting the sign right. If you look at the sign, say, of a product here, on the left we've got E1, E2, F2, E4. On the right, got E1, F2, E3, E4, F4, etc. To get the sign, you have to take the E1 on the right, anti-commute it past three things on the left, annihilate it with an E1, and keep doing that until you've got everything back in your canonical order, and you've got to count the number of swaps, and count the number of times that an F is squared to -1. Now, counting the number of Fs is easy, because you do that with a bit mask. But counting the swaps is actually quite painful. It was particularly painful in Haskell that didn't have any access to underlying binary representations. You actually had to encode, convert everything back to decimal, so which made it particularly slow. But even with the raw access to kind of raw binary operations, there's no simple way of taking these two blades and counting the number of swaps when you multiply them together. What we did in our original Maple implementation was use lookup tables, which back in the 90s that was fine, but these days lookup tables are just a dreadful way of trying to get any kind of performance out, because you've wasted about 30 plus clock cycles just getting this thing from memory. I spent some time when I was at ARM, what kind of kept me interested there was the thought that it might be worth designing a circuitry to do this particular computation for it, this counting thing. But then I realized that that's just a spectacularly bad idea for lots of reasons. One of them is this is just not a great way of implementing the small geometric algebras. And secondly, I found a way to do that doesn't involve changing the hardware at all. It just works in existing hardware. So fortunately, ARM didn't waste any time on this. So this is the next trick I want to talk about. This is a slightly different way of encoding blades in a binary representation so that getting the sign of the product is straightforward. And it comes back to this conformal split relation. The idea that the algebra G P plus 1 Q plus 1 is a direct product of G11, which is actually a 2x2 matrix, if you like, and GPQ. This is what David called the conformal split. And this was actually how David introduced conformal geometric algebra in the first place. The way this works is you start off with your EI and FI, little EI, little FI basis vectors, and you introduce these new trivectors. Capital EI is now say capital E1 is E1 times En Fn, where En and Fn are the little generators of your conformal bit. Similarly for Fi, these capital E's and F's are trivectors, but they still satisfy the correct generator relations. Actually, the EI squared to +1, the Fi squared to -1, and they anti-commute with each other. So they generate a new algebra. They generate the algebra GPQ. And because of the way these are constructed as trivectors, the capital E's commute with everything built from the little e's. So these two algebras now commute with each other. And this is another example of how you need to be a little bit more flexible about grade. So these trivectors, E's and F's, they're grade 3 objects in the large algebra, in what you might think of as the conformal algebra. But in the smaller algebra, they're vectors. So they can be trivectors in one space, vectors in another interpretation. Actually, this makes complete sense geometrically into the conformal geometric algebra, because these trivectors we would think of as lines going from the origin through the point of interest and out to infinity. That's what the trivector represents. So it makes complete sense that when you're trying to go back to the smaller algebra, it's those lines are the generators, they're lines through the origin. That's what we think of when we're doing, say, G30. We tend not to do the split this way anymore. We tend to do the split via an embedding. But this actually was the way David originally thought about it, and there is some advantage to this. The fact that these algebras commute is definitely an advantage. So what I've been doing is using this trick as a way of decomposing the balanced algebra, so GNN, which is quite a good one to implement because it contains everything within it. Using this trick, GNN can be decomposed into a whole set of commuting subalgebras. But the generators have this slightly odd behavior that the generators of the next one are trivectors in the space, and the generators of the next one are 5 vectors in the space, and so on. But each of these little blocks is a copy of G11, and they all commute with each other, and that's a huge advantage, which I haven't seen exploited a great deal up till now. So this gives us a slightly more complicated binary representation of objects, but it's one that's going to give us a great deal of speed up. So now there is the binary number 1 represents E1 and 2 represents F1. But the number 4 doesn't represent E2 anymore. It represents E2 times N1. Number 8 represents F2 times N1, and so on. So it's a slightly more complicated encoding. So if we then want to get the vector F3, that's actually represented by this binary number now. But the big advantage of this is that everything commutes, so that when you've got taking a product of 2 of these blobs, you can kind of line them up on top of each other because all the other bits have commuted past each other, and all you have to work out is the correct sign for each of the individual products now. That's a product within this valence algebra. So this is one of those Cayley tables for G11. And what we care about is when do we get a minus sign in this? And you get a minus sign when the first entry contains an F and the second entry is a vector. So that's a much easier thing to implement as a binary test. We want the first term to contain an F, so that just means we take an AND between our first element and 1, 0, 1, 0, 1, 0, 1, 0, etc. And the second term needs to be a vector. And that can be done by shifting left and doing an XOR, and then just seeing if we have a 1 in the second or fourth or so on slot. And then the final thing is you do an AND between that and the first vector, and that, whether that's even or odd, tells you whether you need a plus sign or a minus sign. So all of these are very, very simple binary operations. They're all available for a sort of low-level languages like C and Julia can just implement these. And obviously they're blindingly fast because they're just bitwise operations. And this whole thing, it actually just ends up as being sort of 3 lines of code. So this gives you a route now to implementing the general product of two arbitrary elements, where the way you store these now is a list of the basis elements that are present in the multivector and a list of the float values. You can go in and you can do the multiplication very, very fast. The problem is addition's a real pain here, because you end up with a big set of resulting blades and resulting numbers. Those blades aren't in any canonical order, so you have to do some sorting, and then you have to see whether you've got two blades with the same coefficient and add them, and that's the part that is really, really slow. And I haven't got a really good answer for how to do that efficiently at the moment. I'm not sure anyone has. What I do for, say, G44 is I actually just rather crudely temporarily expand to 264 components, add those two vectors and sparsify back using a kind of sparse library that Julia has. But it isn't brilliantly fast. For G3232, this is where I'm using 64-bit ints as the representation of the blades. This approach isn't even available, so you just have to do some sorting stuff under the hood. So this does turn out to be quite slow. This is not a good way of implementing geometric algebra for those smaller algebras, the ones that we've kind of been talking about a lot today. But it's not desperately slow. It's still, it's still a few 200 nanoseconds to a product, so it's perfectly good for most of the applications we want. But it's not the way to really squeeze optimal performance out. So for example, a quaternion multiply, I did this on a different laptop, but 20 to 30 nanoseconds doing it in G30 is a sort of native operation. About 600 nanoseconds if you work in this fat algebra, encode two quaternions there and do the multiplication. So it's a fair chunk slower. I think there's still a lot of room for improvement, and this actually how you write this stuff efficiently is still a bit of an open problem. Okay, so I've got 3 tricks so far. I've still got 4 to go, but these 4 are all quite similar, and Joan's already kind of presaged one or 2 of them. These are all to do with rotors, bivectors, exponentials, and so on. I was in a sort of discussion thread recently where people I was talking to did not agree with this approach to implementing geometric algebra, because for them, geometric algebra is all about interior products, exterior products, basically kind of Grassmann algebra, if you like. They didn't care about rotors, so they didn't care about these type of optimizations. But I think for most of us, we would, when people say what's the unique thing that geometric algebra has that nothing else has, it's rotors, exponentials, and bivectors, and so on. That's the real special secret sauce. And actually, in some cases, exponentiation can be quite hard. Stephen, are you going to talk about exponentiation in? Okay, right. Yeah, these can be quite hard to implement. So when I first talked about this library back at the last conference, the request came from the audience was very much you have to implement an exponential operator. So I've implemented an exponential and a bivector exponential operator. But when you get up to things like conformal geometric algebra, this actually gets quite slow. The problem in CGA is you're exponentiating a bivector. This bivector squares to a scalar and a 4 vector. That scalar can be 0 or positive or negative. The 4 vector can also have a square that is 0, positive or negative. You end up with this quite ugly branchy code, lots of if statements. They're generally not a good idea at runtime. If you can avoid them, you're going to get something more optimal. So I was led to this trick that I'd never seen before, but I guess it's probably something that most computer scientists maybe learn. I thought so. So it's surprisingly effective, far more effective than I kind of thought it would be. So if we try to exponentiate the bivector b, what we do is we find the power of 2 so that b divided by that power of 2 has a magnitude less than 1, so that when you exponentiate, you can implement that with a Taylor series. After about 10 terms, you've got something with magnitude less than 1 to the power of 10 divided by 10 factorial. You've got something that's vanishingly small. So you can truncate your series there. So that's just 10 geometric products. That's very quick to do. And then finally, you need to raise the result back to the power of 2 to the n, but that's just multiplying yourself by yourself n times, which is another n multiplications, and not many. And that gets you the result. I was just kind of astonished to see this, because I'd never come across it before. Really, really neat. So I've implemented this in the cases where the product is hard to do via other ways. And certainly by the time up to CGA, this is really good, really effective. And apparently this is actually what's going on under the hood inside your computer when you actually ask it to exponentiate something. It's using a version of this and some other lookup table and stuff and other bits of magic. There's two further tricks that Joan talked about a bit as well, to do with rotors and normalization and the ability to add them and scale them and so on. And there's a particularly useful result that works up to 5 dimensions, which is following. Rotors are even elements. So they're even elements with 2 properties. First one is R reverse is 1, they're normalized to 1. And the second key property is that psi A psi reverse, the sandwich, returns a vector. Now, in general, in larger spaces, that is not guaranteed. But actually, up to 5 dimensions, you can guarantee that psi A psi reverse will give a vector, or RA reverse will be a vector provided R reverse is 1. So you've just got 1 test rather than 2, which is actually quite useful, because that second thing is a very, very hard thing to test in practice. And there's a little proof there that you can check if you want. So that gives us another way of actually our users get a little bit more accuracy out of that numerical exponentiation calculation, that if you have a psi that you hope's a rotor, but it's drifted off a little bit from being a rotor numerically, all you need to do is renormalize it by computing psi psi reverse and then dividing by the square root, or one of the square root of that. Because you're close to 1 anyway in that normalization, that square root you can truncate after 1 term. And this improves the accuracy of the exponential formula even further. It's just using this trick that we use quite a lot, that even elements, once they're normalized, give you back a rotor. And the nice thing is actually, you can go through a mathematical proof and show that that is the correct thing to do. That is the closest rotor to psi, given that you want to get to something that is normalized to 1. Typical application of this is, let's say you're defining some camera motion with keyboard and mouse input. The way I like to do that is each time you kind of press the key or move the mouse, that's a bivector, a conformal bivector, a PGA bivector typically in this case, sent around. You then get a small change to your overall rotor that controls the pose of the camera, which you add in as a 1 plus b, then you multiply that by your rotor at step I. The new rotor is then, take that psi, normalize it so you're back to being a pure rotor again, and that gives you the rotor at the next position. That's a really, really fast way of implementing camera control. Similarly, you can use this to get a very fast version of slurp, so a spherical interpolation. You need that to correctly interpolate between 2 rotors, because the path between them is generally a curved path. But you can use a little bit of algebra here to show you that the midpoint rotor between, say, 2 rotors R1 and R2, in these low-dimensional spaces, you can get just by adding the rotor and then dividing by the magnitude. And that is the correct mathematical interpolation of 2 rotors. They could be rotations, translations, etc. Up to 5D, this implements that very, very efficiently. That gives you the midpoint of the slurp. If you want to do more accurate slurp, you can just do a few more midpoints until eventually you can lerp between them, and then the lerp formula is fine. You just do a linear interpolation and normalize the result. And that gets you a nice smooth path between various pose elements, which is very handy for, say, animations, that sort of thing. And the final one, this is coming back to CJ, conformal geometric algebra, which I actually ended up using quite a lot now, is suppose you're in CGA and you're working in one of the spaces where there's an invariant, whether it's E bar, or N. So it could be N over in Euclidean space. N will be a null vector. We've got 2 points, X and Y. We want to find the translation between them. Then this T, which is YGXG plus GYGX, is the unnormalized rotor that does it. And the normalization is just a scalar in this case. It's very easy to get, if you even need it. One of the nice things of being in a homogeneous space, you probably don't care about scalar normalizations quite often. There's a short little proof, and actually this is quite a fun thing to play around with, because once you see that that's the rotor between them, you can go into spherical and hyperbolic and Euclidean space and get the distance between 2 points from the amount of this rotor that goes around. It gives you quite a lot of insight into where the various distance formulae come from. Okay, so I've slightly exceeded my time. Yes, sorry about that. So summary, particularly for people kind of coming into the field, these are the things that I'd like you to think about. Please focus on applications. I really don't want to get any more emails from people saying they want to do GA research with me. I don't even know what that means, actually. Pick a problem and solve it. Don't get stuck in one algebra, and definitely don't get stuck in fights between whether one algebra is better or worse than another algebra. You should be able to understand all of them and pick the one that's appropriate for a particular problem. And you should be able to move between them, and you should write code that enables you to move between them. One of the things that has been a stumbling block for people that hopefully isn't a problem for the sort of next generation coming through, this idea of sum of the vector squaring to 0, sum squaring to +1, sum squared to -1 is a bit weird at first. It's less weird to physicists because we're used to it from special relativity, but that's weird to us when we first meet it as well. So it's weird to everyone. You just kind of have to embrace it. It's just where a lot of the interesting algebras are. They just have this mixed signature space. In fact, I think it's the key thing that Clifford didn't have in his original work, that he missed, that would have enabled him to go a lot further. That and the fact that he died straight after he put his first paper out. Not much you can do about that. Grade is a flexible concept, so don't get too hung up on whether particular things mean something. They may mean one thing in one algebra or something else in another algebra. It's probably worth learning the matrix representations, but don't fret about them too much. You can just look them up, but just be aware that they kind of exist and there might be some useful information in them. Those tricks I just showed at the end there, they are all part of a kind of standard game developer's toolbox to avoid doing any trig or log or exponential calculations if you absolutely can. Rotors are very, very good for avoiding taking exponentials and so on. Because they avoid working with the Euler angles for, say, 3x3 rotation matrices, that gives them a lot of performance boost. If you are writing your own code, make it easy to move between algebras. I think this was something that we did wrong in our early implementations. So you want to be able to have multiple algebras in flight simultaneously. And keep your API clean. I think if people just write code where you've implemented a geometric product, a projection, a reverse operation, and a take a scale apart operation, you're kind of done. Just do that as a base layer and then build on top of that. And if there are any hardware guys in the audience, if you talk to any hardware guys, just give us quaternions. Hardware guy, I've talked to you about quaternions. You don't need to be told that. Okay, and finally, if you're interested in looking at the code, it's up there. It's still being tested at the moment. It's not, so a couple of little gnarly bugs in it, but welcome to play around with it if you're interested in Julia. I do recommend Julia as a really interesting language to look at. It's very kind of future-proof, I think. Contact details, there is a Twitter handle for the last few remnants of people that still bother with Twitter these days. Thank you to Monumo for allowing me to just do all this stuff on their pay, which is very good of them. And also, yeah, thank you to the organizers.